Hello everyone, myself Shinde V.G., working as Assistant Professor at Department of Nanoscience and Nanotechnology, KTM College, Nashik. Today we are going to discuss T.Y.B.Sc Semester 3rd, paper number 5, that is the course of Energy Conversion Devices and Applications. In today's lecture, I have covered the design of photovoltaic solar cells. In the design of photovoltaic solar cell included in this topic, I have covered in this lecture some topics. First one, the solar cell design, design for high ISC, anti-refractive coating ARC, design for high VOC, and last one, design for fill factor. These points I have covered in this lecture. Now, the first one discuss with solar cell design. A solar cell must perform the following three functions as efficiently as possible. First one, absorption of light, separation of generated change carriers, and transport of separated charge carriers to external load without resistive losses. That's why the solar cell perform means working of the three main factors or three main functions of effectively possible. That's one. The first one, absorption of light. Solar panel, some materials are used, the material properties are defined that the absorb more than more light. Another one function is the separation of generated charge carriers. And the last one function is transport of separated charges. Without resistive losses have the external load or apply the external. That's how the solar cell is must be performed for good performance. Solar cell of a given material must be designed to maximize the light to electricity conversion efficiency. Means the material designed by the maximum light to electricity conversion efficiency. That's how these material are used to solar cell. This in turn requires optimization of solar parameters such as ISC, VOC, and fill factor such that higher values of each of these are obtained to get high cell efficiency. Mean in solar cell optimize of solar cell parameters. First is ISC, second VOC, and fill factor. Higher value of each of these are obtained to get high cell efficiency. The cell efficiency is written as neta is equal to ICH into VCH into fill factor upon PIN. That is the equation number first. They discuss the design issue in order to manufacture an efficient solar cell. These solar cells are manufactured that some issues that's the discussion of the solar cell design by issue that the manufacturing of efficient solar cells. To design vapor-based mono and multicrystalline silicon solar cells, the design for mono and multicrystalline silicon solar cells by a vapor-based. That's how silicon is the most commonly used material for commercial production of solar cells. Silicon cost is low, that's how our performance is good. That's how these silicon materials are commonly used at the production of solar cell. The design of solar cells points we have covered. First one I have discussed the design for high IC. the expression for the short circuit from which the requirement for obtaining high ISC can be reduced is as follows. Means the short circuit current from the requirement obtaining by the high ISC is equation we have find out or we have produced by the ISC. ISC is equal to Q capital AG in bracket Ln plus W plus LP. The ISC is the proportional to the cell area. Therefore, large area cell will produce large current. They have the large area produce large current. That's why all generated charge carriers should be separated by the p-n junction. Therefore, the p-n junction should be close to the point of carrier generation for efficient charge separation. These p-n junction should be close point of charge generation for efficient charge separation. The orientation of the p-n junction is also important for large ISC. The p-n junction is also important that large ISC. Now the design for high ISC is point over that. Now a most important point of anti-reflective coating means ARC is discussed here. Now an ARC is a thin layer of a dielectric material deposited on the surface of solar cell. This is the one of technique of thin layer deposition. This deposition by a dielectric material deposit on a surface of solar cell. Solar cell surface deposit by thin layer, very thin layer by technique use that the anti-reflective coating. It should not absorb any light and should reduce the reflection. Here silicon surface refer about 30% of incident light. They have which use that is the it is not absorb any light and should reduce the reflection. These are the properties of anti-reflective coating material or anti-reflective coating dielectric materials. That's how the silicon surface refer about 30% of incident light. 30% of incident light. That's how more than use or commonly used that silicon material. The reduction in reflection is based on destructive interference. The reduction in reflection is based on destructive interference. In order to obtain the condition of destructive interference, thickness D1 and reflective index N1 of the ARC should be properly chosen. The thickness of the dielectric ARC should be such that the radiation reflected from the air ARC interface and from the ARC semiconductor interface have a 180-degree phase difference. Means the thickness of dielectric ARC should have radiation reflected from air ARC interface to ARC interface from ARC semiconductor interface have 180-degree phase difference. The out of phase waves will have destructive interference resulting in zero for small reflective energy. This requires that for the normal incident, the thickness of the ARC should be quarter of the wavelength. That is, the equation of D1 is equal to lambda 0 upon N1 upon 4 is equal to lambda 0 upon 4 N1. Where lambda 0 is the wavelength of radiation in air and lambda 0 upon N1 is the wavelength of radiation in dielectric medium of refractive index N1. That's how the lambda 0 is wavelength of radiation in air medium. and the lambda 0 upon n1 is the wavelength of radiation in dielectric medium of refractive index n1. It should be noted that the ARC choose according to equation first will given minimum reflection only at a certain wavelength lambda. For other wavelength of the spectrum, hence the thickness of the ARC layer should be chosen such that the reflection is minimum at the wavelength where solar radiation intensity is maximum. Means the thickness of ARC layer should be a reflection is minimum at the wavelength where solar radiation intensity is maximum. Means here is the inversely proportional relation. That's how this happen between 500 nanometer and 600 nanometer for AM, the 1.5 solar spectrum. The minimum reflection R mean can be written in terms of N0, N1 and N2 as the equation is R minimum is equal to is reflection minimum is equal to in bracket N1 square minus N0 into N2 upon N1 square plus N0 into N2 bracket complete raised to 2. That's how finding formula of the reflection of minimum. The R mean will be 0 if a following condition is met. N1 is equal to under root N0 N2. That's how the condition that the glass and silicon have refractive index of above 1.5 and 3.8 respectively. Means the refractive index of glass is 1.5 and silicon is 3.8 respectively. They have the diagram showing that minimizing of refractive losses by putting anti-refractive coating ARC of a thickness D1 and refractive index neta. This is the figure showing that first one. Okay, and B figure is a surface texturing. That's how the texturing surface. First one, the incident light by the ear glass N0 ARC D1 minus N1 in here. Okay, semiconductor N2 material. That's how the minimizing of refractive losses by putting anti-refractive coating ARC of thickness D1 and refractive index neta in here. The B figure showing that the surface structuring. That's how the pyramid. This surface they have the pyramid type. Okay, this surface they have pyramid type. That's how the surface structuring, and the figure 3 is ARC with surface structuring that. This is the showing that figure. In here the anti-refractive coating point is over that. Now discuss with the second most important parameter of solar cell design is the design for high VOC. In open circuit voltage of a solar cell is mainly governed by the recombination in the solar cell. That's how this implies that higher VOC can be ensured by minimizing recombination in solar cell. This high VOC implies that the ensure by minimizing recombination in solar cells. The VOC is defined as the voltage at which ISC because equal and opposite to the forward bias diffusion current due to bias of junction of photovoltaic. That's how the VOC at the voltage at which ISC. That's how the VOC because the equal and opposite to the forward bias diffusion current. That is the known as VOC. That's how the bias of junction of photovoltaic. The forward bias diffusion current depends on the recombination at the surface in the bulk of the solar cell. This is the forward bias diffusion current depend on the recombination of surface and in the bulk of the solar cell. That's how depend on forward bias diffusion. Any increases in recombination gives rise to increase in inverse saturation current Ise. Solar cell IV curve is reproduced here. I is equal to I0 in bracket e raised to qv kt minus 1 bracket complete minus IL, I suffix L, not IL in here, I suffix L. Thus, the increase in I0 due to the increase in recombination results in increase in forward bias diffusion current for the same forward bias voltage. That's how the I0 due to increase in recombination results. That's how the increased forward bias diffusion current and the sum forward bias voltage. Means the increase in I0 means the increase in recombination. That's how the increase in forward bias diffusion current and the forward bias voltage is also increases that. Then, as per the definition of the VOC increase, recombination in solar cell decrease the VOC of the cell. Means then, as the per the definition of the VOC increase recombination in solar cell decreases the VOC of the cell. Means the recombination increase by the definition of VOC, the increase recombination in solar cell decrease the VOC of the cell. Means the inversely proportional relation that the VOC are decreased, that's why increase the recombination, or recombination is decreased, VOC is increased. That how the number of minority carriers at the edge of deflection region is due to ejection. That how thus minimizing minority carriers ejection implies that the minority equilibrium carriers concentration should be reduced. That it can be obtained by high doping at both the side of the junction. This figure showing that the minority carrier lifetime and the Doppler level. This here the recombination by traps and the variable as per material quality. Okay, the agar and radioactive. That's showing that the graphical representation of the minority carrier lifetime. Okay, now discuss with the design of solar cell. That's how most important parameter or last important parameter is the design for fill factor. Apart from maximizing absorption for high IC and minimizing recombination for high ion, I suffix L, and VOC resistive losses should be minimized in the order of to get high efficiency. Let's have the first one I have discussed the high recombination by the or designed by the high IL. That's how here the absorption for high IC, the maximum or high absorption for high IC and the minimizing recombination for high IL, and the VOC resistive losses should be minimizing in order to get high efficiency. That's how in resistive losses are the result of series and shunt resistance of the solar cell. Both of them affect the fill factor of the cell. Means in previous lecture I have also discussed the series and shunt resistance. That's how these resistance affect or this resistance effect that the oppose or affect that the fill factor of solar cells. Okay. The series resistance of a solar cell should be as low as possible. then the series resistance should have the solar cell can be this value is low possible, and the shunt resistance of a PN junction should be very partial of the junction. That's how the shunt resistance of a PN junction should be very partial of the junction, which lowers that shunt resistance of the cell. The shunt resistance is not a design parameter. Means the shunt resistance is not the design parameter. It should be leakage of the path with the parallel with current source. That's how it mainly the series resistance that is overhand a design parameter. Means the series resistance is overhand by the design parameters. The series resistance RS of a solar cell is made of several components. These included components of several components of the design of series resistance. These included resistance components, it should be written here. The included resistance of a base is denoted as RB. The resistance of emitter is denoted RE. Thinner side of the junction is referred as emitter. Okay, thinner side of junction. This is referred as emitter, and the resistance of metal contact at the front and the rear RBF, and resistance of the metal semiconductor interface or contact resistance RC. That have the rear resistance. Rear resistance means the resistance of the metal contact is denoted as RBF. Okay, and the contact resistance is denoted as RC. These components are showing in figure. Figure is showing that the next slide. These components ISC can be written as the design for series resistance is depending on these components. The series resistance is can be written as RS is equal to RB plus RE plus RC plus RBF, means base resistance plus emitter resistance plus contact resistance plus rear resistance. That's how this calculated or this addition that these components of these resistances. Okay, that's how to design the series resistance RS. Okay, now in figure showing that the emitter base then rear contact in here, and also denoted that RB, RE and RBF. That's how this figure a three-dimensional simplified structure of a solar cell depending on the direction of a current flow and component contribution to series resistance. This resistance we have contribute that or this design that the series resistance of the material. In this lecture, I have discussed the design of photovoltaic solar cells. In photovoltaic solar cells, they have most important three parameters it should be studied. First one, the design for high ISC. In this point also included the most one point is include that the anti-refractive coating. These coating are used for the thin layer dielectric material deposit to the solar cell surface or surface of solar cells. Okay, then another one most important parameter is design for VOC, and the last one important parameter is design for fill factor. Thank you.